Hello, everyone. Welcome to the MIF++ seminar. It's a pleasure to introduce Professor Wolfgang Hornfeck, who will talk about chiral spiral cyclic, twins or snowflakes. He will explain. Over to you, Wolfgang.
Yeah, thank you, Vitaly, for inviting me to give this talk. I announced it under the title Chiral Spiral Cyclic Twins. But of course, due to the time of the year, I think one could replace the twins also with snowflakes. And I want to show what I mean with this. The outline of my talk will be, first off, I will give a general idea. I will talk a little bit about cyclic twinning. And then I will mainly focus on two things. One experimental result of nickel zirconium, which started this whole business. And then, of course, I will talk about the chiral spiral cyclic twins, which is more mathematical model. And in the end, I will shortly give some potential applications and also mention shortly another example, that of cyclododeca sulfur. So what is the snowflake science about? There are like three previous papers, one starting very early in 1611 from Johannes Kepler. It happened that he was also at this time in Prague, and he published a short booklet about some New Year's gift to his patron at this time, about snowflakes and how they are composed of little tiny spherical entities. So at that time, of course, atoms were not known, but he had some idea about packing spheres, and that's maybe the start of crystallography anyhow. Then, of course, there is a paper from Alan McKay from 1981, where he references this original work from Kepler, but with a twist, because he's talking about pentagonal snowflakes, of course, in the context of, say, what we now call quasicrystals, but of course at that time they were not discovered yet. And then there is this paper from Aloisio Janner, who also talks about the ordinary snowflakes, but also with a twist in that he talks about the dendrites. And in some sense, I think all these things are connected to my talk, and they follow all this principle of AGI, which in this context does not mean artificial general intelligence, but the three words abstraction, generalization, idealization. So this is, I would say, the shortcut of my talk, the general idea. So let's say a little bit about these three people. So Kepler, of course, he's known as astronomer, but he's possibly also the first crystallographer. Like I said, you see this picture of these spherical entities forming some packing. And definitely he was like an idealist, because he developed this model of these Platonic solids with circumscribed and inscribed spheres to explain the cosmos. This is all well known, of course. Then there is Aloisio Janner. He was also extending crystallography. Mainly he is known for this aperiodic crystallography of incommensurately demodulated compounds, inventing the superspace description together with Janssen and de Wolf. But he also was focusing on snowflakes and also on these biological macromolecules, on these viruses. And he wanted to explain them with, say, either new symmetry operations, like hyperbolic symmetry, or he wanted to explain them with these integral lattices, like explaining these shapes with integers, in fact. And then there is, of course, Alan McKay. Unfortunately, he passed away this year, so there is a special commemorative issue of the journal Structural Chemistry as of this month. And he was also, of course, trying to generalize crystallography as a science of structure, and something not only based on space group symmetry. So these are the three people, say, who are like the inspiration of this talk a little bit. And McKay, for instance, found some patterns in other contexts too. So this is a plot of the date of Easter. So Easter could be seen as a symmetrical festivity to Christmas, of course. And you see the regularity in the data of ISA. It's almost like a lattice. But of course, it's not really like a lattice. There are some deviations from really a lattice symmetry, but still it's pretty much regular. And this is, of course, due to the fact that there are 3 astronomical periods working together in the definition of E star. This pattern was possibly first plotted by some French astronomer, Flammarion, and he also showed this kind of picture. And this is the final part of this general idea. So this is how I see myself. It's like you see these patterns like the stars on the sky, and then you try to figure out some hidden mechanics in the background and what's going on to describe these patterns everyone else sees in plain sight. So this will lead me to a few words about twinning. So twins are by definition the oriented association of 2 or more individuals of some crystal. And these 2 or more crystals are related by some symmetry operation. But the symmetry operation is not contained in the crystal itself, but it's a symmetry operation of this twin entity. So you see here the example of this contact twin, where you see this highlighted phase. This could be some mirror plane, for instance, or you see on this side the cyclic twin, which shows how these crystalline phases can repeat after some finite number of rotations. So the idea is that, of course, twins are more general set of entities, and cyclic twins are a subset of this general set. And spiral cyclic twins are, of course, a subset of the cyclic twins. So it means that not every cyclic twin is a spiral cyclic twin, but the opposite, of course, is true. You find some of these examples in nature, very nicely looking. It's not so common, it's quite rare phenomenon, but some materials are known for it, like rutile. They show it quite often, and also chrysoberyl and these other examples. You can find it in synthetic nanoparticles of gold or diamond very often. And there are also, if you think more general, there are also these kind of ideas in for instance, in biology, when you have the structures of some zooplankton. This also uses some, say, cyclic twinning to construct itself. And also you see this virus particle, which also can be somehow seen like this kind of process in action. From a technological point of view, these cyclic twins are mostly not very welcome. So you can think of a material like quartz, for instance, which is known to be enantiomorphous. So it occurs in left and right-handed crystals. And this property of chirality is coupled to the property of piezoelectricity. And this is, of course, responsible for some nice properties quartz crystals have. But if you introduce some inversion symmetry, this red circle, and you twin these left and right-handed version of your crystal, then, of course, you destroy this chirality. So this is not much liked, of course. You can also see it in a solder material. It's like a lead-free tin solder material. And when you process it like it's written there, you also get these cyclic twins. And this, I guess, is also not very welcome for the properties like using this solder material in electronic circuits. This brings me to the tenfold twins of nickel zirconium. So this started, in fact, as a project of materials research some years ago when I was a postdoc in Cologne at German Aerospace Center. And they have a special magnet method there, electromagnetic or electrostatic levitation, to process alloys or metals without using containers. And it's a nice method for ultra-pure processing. And in fact, this was not even my project. Also, I worked with intermetallics in my PhD, but I shared the room with some colleague who was working on nickel zirconium as a model glass former. and doing these experiments. And usually what these people do is they measure some dendrite tip velocity, and they have some theoretical models to predict it, and they get these kind of plots. And it's honestly, it's a little bit boring. You know, it's really physics, like say material physics, interested in these properties of these growing crystals. And this is the setup. So for the electrostatic levitation, you have these two electrodes in between this floating metal, and there's a lot of stuff around it. So there's, for instance, like an infrared laser for heating. Also, you can observe the sample with a high-speed camera. And the usual process is you melt the sample far above its melting temperature, and then you switch off this laser, and then you let it cool down. And because of these ultra-pure conditions, it will not instantly crystallize again at the melting plateau, but it will pretty much cool down quite a lot below it. So it can be, say, 300 Kelvin, even below the melting temperature, until at some point it will start to solidify spontaneously in a very short time frame of a few milliseconds, and then you will have a solid again. And usually the solidification is, like I said, it's followed by a high-speed camera setup. Usually the solidification front is like spherical or circular from the outside. And you see it because of the latent heat is released, and this gives some contrast in this high-speed camera image. So you can observe it in situ. So like I said, this process is done in 4 milliseconds, very fast. And like I said, usually this this front is circular, so nothing special. But my colleague observed this polygonal front. And if you count the vertices, it's like 10 vertices, so it's like a 10-fold solidification front. This is already like very weird. When you take out the sample, you can, it's like 2 or 3 millimeter size ball of metal, and you can observe this with an optical microscope. You see that in this case, it looks like a little sphere, like a planet, which has some pole and some longitude lines. So you have, say, these 10 longitude lines, or say 5 great circles on this ball, which allows you to embed this kind of sample in an oriented way. So you can look along this axis. So you embed it into some resin, you cut it in half, and then you observe it with a light microscope, and then you see this nice twin pattern. You can also put it in an electron microscope for the details. Of course, then you see more details. You see these dendrites growing, how they form this twin domain, and the red lines are some twin boundaries. And you can also use the X-rays backscattering to analyze the orientation of individual unit cells of your crystal, so that you can really prove by experimental means that there are 10 domains. I mean, these are false color plots. The colors essentially don't mean nothing much, but you can prove that there are 10 domains oriented like in this twin. And of course, that was when the people started to ask me, can you explain this? Because this is a very reproducible process in nickel zirconium. It always produces these 10-fold twins. And usually these alloys produce like single crystals, or maybe at most some 2 crystals randomly intergrown, but they don't produce this kind of twins usually. Of course, you can first analyze the microstructure more and get some ideas about this twinning. You see that these twin boundaries are always inside the dendrites. You can make these sketchy pictures, which are looking like snowflakes. So that's maybe the motivation for talking about snowflakes a little bit. But this is, of course, only like the microstructure. It doesn't tell you much about the atomic arrangement. So my colleagues asked me, because they knew that I was working in crystallography and structure determination before. So essentially, they asked me to explain this on the basis of the crystallography of this compound. And the crystal structure was long ago known already. So it's not so complicated. It's orthorhombic with 8 atoms in the unit cell. And also the twinning was somehow already observed with electron microscopy before. So there's in some sense nothing special. You can analyze the actual ratio. The B to A ratio is such that you can get some angle of 36 degrees to the diagonal, 36.4. And of course, for tenfold twinning, you would ideally need 36 degrees. So there's a slight discrepancy, but this is nothing much that prevents nature for doing this. What you can also see on a second glimpse is that you have this regular pentagon with one atom missing inside the crystal structure in a way. But this is maybe not so obvious in the first instance. So I played around with this kind of model. I tried to construct these twin domains, like say, like a piece of cake, and 10 pieces of cake giving the whole cake. And then I tried to shift them at the twin boundary to see if there is some good, nice reconstruction of the twin boundary, like a nice fit. And first I tried some crystallographic values like shift of 1/4 or shift of 1/2 and so on. But this was all not very nice. But I finally found a shift that was extremely perfect in the way that you see that there is these red unit cells from the bulk twin domain. And here you see a green unit cell across the twin boundary, which is exactly the same unit cell. I found this very remarkable. And I analyzed it further. You can now analyze it without making reference to these crystallographic shifts. Just I was looking for shifts that give a good match. And I realized that you can use these rhombs in the background to figure out these perfect boundaries. And these rhombs, if you look at them closely, that's the Penrose rhombs, like sin and sig Penrose rhomb. And you can use these rhombs to make this matching conditions for the boundary. So there are several conditions which can give a match, but only one of them is really perfect. This is the one shown on the right, where you have, say, 2 levels of hierarchy, like one is this green Penrose rhombs, and the other one is these red ones, these lines connecting.
Wolfgang, could I ask a question on
Yeah,
this
you have a
slide?
question?
Yes.
I don't hear you, sorry.
Can you hear me? Wolfgang, can you hear me?
I cannot hear you.
Oh, okay. Then continue. Don't worry.
I could hear Vitalis.
Yes.
Can you try again?
Wolfgang, can you hear us? So, yeah, some of us are talking. I'm wondering if.
Can you hear me?
Mm-hmm. Could I ask the question on the previous slide?
Yes.
So with nice pictures on,
Cannot go back.
Yeah,
For
on
some
the
reason.
previous slide.
No. Yeah, this one.
Yes, so with green edges and purple edges, are they bonds, chemical bonds between atoms?
No, they are not. They are just geometrical highlighting. I mean, there could be some bonds, say, between on the red edges, between atoms on the red edges, I guess.
Mm-hmm.
But in this intermetallics, it's anyhow hard to tell if where do you have a bonding, or it's like there could be some covalent bonding, I guess, but mainly it's metallic bonding.
Mm-hmm.
So this is all just geometry highlighting.
Right. So these structures are simulated.
Yeah, well, these are all, say, simulated. Yes, this is the ideal situation, but based on this unit cell of nickel zircon. So based on this kind of unit cell, and we just try to get the ideal structure in the, from the geometrical point of view.
Yeah, but could you perhaps explain the meaning of the black and gray circles and also large and small circles. What are the differences?
Oh, yes. This is like a, say, abstract depiction of this crystal structure. So the gray circles represent nickel atoms, the black circles represent zirconium atoms, and the different sizes of the circle represent different heights in the direction perpendicular to the plane you are looking at. So the bigger atoms are closer to you. It's like this perspective. It's a binary compound. It's like made of these two atoms, nickel and zirconium, in the same proportions, like 4 atoms each. And like I said, these difference in sizes are different in height in your viewing direction.
In the top part of the slide, you have this nickel and zirconium notations and also the coordinate Z. So,
yeah, that's the Z coordinate in the unit cell, exactly.
So Z is towards us, right?
Z is towards you, exactly.
Okay, thank you.
Yeah, this is this abstract notation because this twinning happens essentially in this AB plane. So all of the pictures are somehow neglecting the third direction. I think I have some picture later which shows you the 3D structure. But this is, say, only governing or determining the AB plane structure. And in this case, when it's referring to the nickel zirconium compound, I made these different sizes. In the later cases, I even will switch to one size for all because essentially these patterns are, say, 2-dimensional patterns. And on this transparency, you see that this, like again, this picture of the unit cell on top, on the left top, and then you see these underlying Penrose rhombs. Of course, it's like a periodic structure, so it's not matching, following the matching rules of quasicrystals. And then on the right, you see how these Penrose rhombs can be used to make this perfect twin boundary, so that you really have like a perfect match at the twin boundary, but you see that the unit cells are rotated by 36 degrees, but they are also shifted a little bit. So this is introducing this. This is needed. This shift is needed for the special twin boundary, and the idea is that you can now use. It's of course, say, a 2-dimensional structure, but you can now use 5 vectors, like these blue vectors in the shape of a regular pentagon, to describe every atomic position on this 2-dimensional plane. And this is what's called Z module. So you have, say, a higher dimensional lattice, which you use for describing something in lower dimensions. This is usually used in quasicrystals and usually also in reciprocal space to present the position of the Bragg reflections. But here you can use it in real space. That's one interesting part of it. We then tried very long to get some experimental proof of it, and finally we succeeded with the help of these people in France to get this atomic resolution picture of such a twin boundary, and amazingly enough, it shows exactly our model. So we did not see the center. We don't expect it to be that perfect in nature, but at least this twin boundary is perfectly agreeing to this model we developed on paper first. There is a whole theory about the Z module twinning, which I will not talk about because essentially it's the work of Danny Grazias. And the funny thing is that he worked independently of us. He worked out, say, the theory of how to project these patterns from high dimensions, like it is done for quasicrystals. And only later we realized that we have the material that could be an example for this kind of theory. And so this was a nice observation. And the Z module theory is much more general, say, in describing not only twinning, what I'm talking about, but also kind of other type of defects and even, say, like new kind of dislocations in this special kind of material. So this is where it all could have ended. So you see this twin again in the middle. It has even something what could say a quasi-crystalline nucleus. Then you see this twin. You can imagine that this twin will grow to in a bigger way to these dendrites with these twin boundaries inside the dendrites. And this explains essentially the observations in nickel zirconium. And as I said, this could have already been the end of it. But if you look closer at this pattern, you possibly observe that these black dots, these big black dots, they are arranged on a spiral. And of course, also the big white dots, is essentially all the dots are, say, arranged on some spiral. And I use this, I observed this first, and then I used it to make the pictures of these twins, to parameterize these twins, because when you want to write an article about these twins, you have to make nice pictures. They should look perfect, of course. And how do you make them without always drawing them manually? It's quite tedious. So you want to have a nice scheme to produce these twins on command, also with, say, different shifts or with different properties. Here again, just to highlight this special situation at the twin boundary, the red unit cell shows you the twin unit cell in the twin domain. The green unit cell is across the boundary. They are identical. And this is not the common case. On the left side, you see some work from Sten Andersen, where you see that usually when you have this cyclic twins or cyclic intergrowths, you create a new crystal structure at the boundary. And also in the center, but here it's different. This is possibly the reason why this twin is so stable, also because it has no energetic cost to create this kind of boundary. Of course, you can also detect some long-range order if you go to reciprocal space. It has some features of quasi-crystals in the sense that it has this tenfold symmetric diffraction pattern with X-rays, and you also see some scaling symmetry, which is usually known for quasi-crystals. So these twins are funny intermediate animals between quasi-crystals and periodic crystals. This is a three-dimensional impression. You see the AB plane, you see the spiraling. This can also explain their growth. It's well known that screw dislocations are usually invoked, say, for some parts of crystal growth. And you have this here in the AB plane. And you also have a mechanism to extend this in the C direction by these pentagonal antiprismatic columns. There is just to say a little bit about the chemistry. There's a lot of compounds crystallizing in this chromium boride type structure, more than 120. All these kind of elements make this kind of binary compounds with this same type of crystal structure. So it's quite common. And you also see that there is some variability in the actual ratios. So these little squares are experimental data from all the crystallographic databases. So you see that there could also be some twins with 9-fold or 8-fold symmetry, which in the beginning was just a hypothesis, but in fact, my colleagues found them in nickel gadolinium. They found a 9-fold twin, not as impressive as in nickel zirconium, but still you can see it. Of course, it's a different chemical system. It has different properties. It's maybe has some impurities, more difficult to process. And also in nickel boron, they found this 8-fold twin. So essentially, you can see this happen more than once for different compounds. And then, of course, when you have these 8-fold, 9-fold, 10-fold twins, then you need your model to be general and to explain all these different twins. So you can adapt it to 8-fold twins. You have to change this angle in the middle of the model and also this position of the atoms. But essentially, it's still the same structure type. It just is a little bit in a different actual ratio, and the atoms are a little bit squished. You also see it for the 9-fold twin. And then, of course, you see that there are these spirals. So when you go from the outside and go inside, you see that there are these atomic spirals. And the goal was to explain these spirals. Or for me, the goal also was just to create some nice pictures with a nice mathematical parameterization. So that leads me to the topic of the talk, the chiral spiral cyclic twins, which are now totally mathematical. They are not related, say, to any structure in nature anymore. And it's just a mathematical model now I want to describe. So how do you do this? First of all, now it's a two-dimensional problem only. And if you have a two-dimensional problem where you have rotations and scalings involved, it might be a good idea to use complex numbers to express these symmetry operations, because that's what they're naturally encoding in this polar form, of course. So we have these complex numbers here, which are the base unit, and you get another complex number out of a combination of these base complex numbers. So you can use the complex number 1 to rotate the whole thing, and you can also use complex numbers to build up such a spiral. There are some other parameters involved. It all looks not so nice, in fact, a little bit cumbersome maybe. The essential thing is that you need two things in your model to specify. One is some circumradius rho, and one is some inclination sequence kappa. So these are, say, the two things where the difference in these different chiral spiral twins is hidden. The framework, so to speak, is always the same. This inclination sequence is like an integer sequence. You can define it with some integer functions, the modulo function and the floor function from number theory. And as I said, you need some parameters, integer parameters, for specifying the sequence. It all looks very weird, maybe. Maybe some of you see that this T of J function is some hidden quadratic formula hidden in there. And maybe you see in the denominator of the beta function, this 2t plus nu is essentially deciding between odd and even numbers. So there is some geometric explanations to these functions. But the algebra looks a little bit horrible, I agree. So what is behind this? So I said you use complex number for specifying the positions of these atoms. And what you do is you have essentially these mth roots of unity. So for instance, here you have the 7 roots of unity, like the vertices of a regular heptagon. And you can just describe them with a complex number and all its exponents. And you can now construct such a spiral of this twin by adding these base vectors, these blue vectors. But you also have to specify the starting point of the spiral, that's this green vector. And you also have to specify, when you want to have an m-fold cyclic twin, you have to make m copies of one spiral. So the model describes essentially the position of the atoms on one spiral, and then you just rotate them m times to create the whole twin. This last rotation is somehow trivial. So the magic is hidden in the green and the blue vectors. As I said, you need some parameters to specify these things. So of course you have to fix the number m for your m-fold twin. If you want to have an 8-fold twin or a 10-fold twin, that's just an integer and say a natural number. And it turns out that you cannot use numbers smaller than 5. So these kind of twins start at 5-fold twins. And then you have 3 other integer parameters, which are usually taken from some small subset of the integers, either 1 and 2 or -1, 0, +1. So these are encoding some properties of these integer sequences. When you combine these possibilities, when you fix m and fix mu, then you have essentially 6 different classes of twins. One turns out to be very similar to another one, so essentially it's only 5 different classes. But you see there is a pattern in there. There is some of the twins, like at B and E, they are straight lines. All the other twins, the spirals, the orange spirals, move in alternating ways. So this is what you specify in the model essentially. Like I said, you use these exponents of these complex numbers to specify some orientations in the spiral where to go next to the next atom. And these exponents are integers. So what you get is an integer sequence. So you get this kappa sequence, like 1, 0, 1, 2, 3, 2, and so on. In this case, it was some alternating sequence. So it's already highlighting some natural breaking points in the sequence. And when you look at this alpha sequence at the bottom, you see that there is this pattern 0, 1, 0, 1, 0, 1, and so on. Some finite pattern of this alternating sequence between 0 and 1s. And if you subtract this pattern from the first sequence, from this kappa sequence, you get this beta sequence, and then you get just some step function. And you see it's increasing from 0, 1, 2, 3 monotonically. But the length of the steps is also increasing. That's the crucial part. It's not like that there's some periodicity inside, but it's some kind of weird local periodicity, if you like. It's always changing. And the farther you go out in your spiral, the longer these twin domains have to be, and the longer these segments have to be. And these parameters I mentioned before, this mu and mu, they are essentially telling you how often you have to repeat these segments, like mu, say 2 times, or if these segments are odd or even in length, that's governed by this nu parameter. And the sigma parameter tells you if you want to use an alternating sequence alpha or if you don't want to use this. So these are these 3 parameters which define this sequence. And you can also only focus on this alpha sequence, say this binary sequence. Then you are like a little turtle who always only knows the current position. And then she can only decide if she wants to go left in a certain angle or right in a certain angle. And when she does it, she updates her new position. And then she does exactly the same. She decides if she wants to go left or right. And depending on the sequences, you get different kind of spirals. Like for different news, you get these 4 different kind of spirals. So this is the way how you can mathematically describe these patterns. There's this other thing you have to know, that's the circumradius in the middle. That's essentially a problem of elementary geometry. You can solve it for each twin individually, but this is quite tedious. When you want to find a general formula, it's a little bit more tricky. In the end, it's based on geometry, and you can just essentially trace it back to some properties of triangles. You wanted to ask something?
Yeah, Wolfgang, could I ask on the previous slide?
Yes.
Did I notice correctly that you had a hexagonal lattice here?
Yes, this is like a triangular lattice, exactly. And this is just to highlight, in this case, this pattern of zeros and ones. That is essentially a decision to make between zeros and ones. So the twin itself is not based on this lattice. It's just to highlight this kind of twofold decision-making process.
Okay, so could you clarify, these spirals, if you continue generating them, they will cover the whole hexagonal lattice completely, or not?
That's a good question. I'm not sure if they can cover the whole lattice in this case. I mean, it looks like they leave out some points. And of course, I think depending on the sequence, I think they can say describe this spirals without intersection, I think. But I think they don't cover all of the lattice now.
Okay, and if you take a different lattice, maybe square lattice, can you apply the same combinatorial rules and generate spirals through points of a square lattice?
I think in principle, yes. I mean, there are some physicists who have done such a thing, in fact, or analyzed such kind of self-avoiding spiral walks on different kind of lattices. So this is like a purely combinatorial or geometrical problem. You can analyze these things. In this case, I just chose the triangular lattice because it's the simplest one. But of course, the twins are living not on these lattices, in fact, but on these CZ modules. So they are not restricted only to triangular or square lattice or hexagonal lattice, but they can live on these more complicated generalizations of a lattice. Yeah.
Okay, thank you, Wolfgang.
Mm-hmm. Yeah, so this is about the circumradius. There are some purely mathematical problems related. You can ask, for instance, if this inner vector can be decomposed into basis vectors too. That would be very nice, because then your whole twin would only depend on one set of vectors, like in this Z module. And you see in this plot of M versus mu that you can do it for the green cases, but not for the red cases. It has some number theoretical property that is involved that decides if you can do it or not. And it's an eigenvalue problem behind it and so on. This is something like totally devoid of any application in crystallography, but it's interesting in its own. It's somehow related to the prime numbers or prime powers of primes, which don't allow this to happen. I haven't really figured out all the details of this. In fact, just to give you an overview, this is some intermediate results when I used only two parameters. Say two parameters are always the same, the other two parameters. And this already shows you the diversity of these twins. Some of them look more reasonable from a crystallographic point of view. Some of them might just be mathematical objects. This parametrization also allows you to highlight different parts of the twins. So you can make some rules like if-then rules to make some colorings. And depending on which parameters you choose in these rules, you can get all these kind of different highlighting, either the spirals or the circular symmetries or the wedge-like symmetries. So this is something I like about this kind of parametrization, that it has some, I think it really covers some essential meaning about this kind of structures. The interesting thing, back again to crystallography, is that there are some degenerate cases. For instance, the case with number 4, which I said it should not exist. Well, it exists, but it shows some overlapping of the positions of the spirals, which I did not like. Usually you want to have spirals which don't overlap or don't intersect. And in this case, they overlap partially. But when you neglect this, you see that the same parametrization essentially recovers all the regular tilings of the plane. There are 3 tilings of the plane, like the square tiling, the hexagonal tiling, and the triangular tiling. And in the same series of parameter development, you also get these other patterns on the right side, which are composed of rhombs, and which correspond to the rhombs of octagonal Amann-Benker quasicrystal or decagonal Penrose quasicrystal or dodecagonal Stumpley quasicrystal. So when you want to make this more clear, here on the left side, I show these twins again, now highlighting these tiles. On the right side, I show the quasicrystals using exactly the same tiles to make the quasicrystals. And in the middle of both patterns, you see essentially with yellow lines highlighted that the core of these 2 patterns are essentially identical. So even the twins have some small quasicrystal patch inside, but then of course at the outside they are really like cyclic twins. They are not quasicrystals. And then I want to say something about potential applications. These twins, you can think of, these are discrete, of course. They are composed of finite a composition of atoms or dots. But these spirals, of course, they emulate something continuous. There's something that's called circle involute. That's a special plane curve, special spiral that you get when you have a string. When you unwind a string surrounding a circular disk. And this is a very special curve. It has some very special geometric properties. So these twins would be examples for this kind of curve. And when you look at the applications of this kind of curve, you find something like, for instance, in the construction, in engineering of nuclear fuel elements in some neutron reactors. So what you see here is the inner part of like the fuel element of the high flux isotope reactor at Oak Ridge National Laboratory. This is some really engineered thing. This is running right now, I guess, producing neutrons. And these involute parts are this nuclear fuel. And the dark lines are empty space for cooling. So this is some engineered example. You might also think about using this kind of patterns outside of crystallography, say for arranging some antennas in this kind of patterns in a sort of phased antenna array. The problem with these antennas is they are directed antennas, and usually you want to direct all the intensity of your antenna in a certain direction into the main lobe. But you also inevitably get these side lobes, which are essentially losing some energy from your signal. And the goal in engineering is to create some antenna arrays to adjust them geometrically so that the side lobes are suppressed. And people use all kinds of different antenna designs. For instance, some aperiodic designs based on quasicrystals to reduce these side lobes to make better antenna arrays. Then, of course, there's an example from biology, phyllotaxis. It's very well known that all kind of plants have this kind of inbuilt regularity using these kind of spirals. Of course, it's not exactly the same spiral like in our cyclic twin, but at least in this cactus, it's also like tenfold symmetric. And of course, you can use these models for this phyllotaxy to compare our twins to these models. The sunflower model also has a very nice parameterization in terms of complex numbers and integers. This is just the integer sequence like you know it, 1, 2, 3, 4, 5, 6, 7, and so on. So that's nothing, it's much more elegant than our model or my model, but still I think I might have the second best elegant model in terms of this. I don't know. And then, of course, my idea was that maybe physicists can use these kind of models for, say, new quasi-lattices for all kind of theoretical physics questions. What happens if you put spins on these nodes? Can you construct topological materials for this? I saw some articles like shown here with this picture, which uses some cyclic twins. You could call it like this, some aperiodic patterns to create these localized edge states. I'm not an expert at all in this kind of physics, but might be interesting for someone to look at it. And of course, you can maybe create photonic crystals out of this kind of arrangements, and maybe they have interesting properties. So I would be very much interested in either mathematicians or physicists who know more about this kind of applications. And finally, I want to finish my talk with another example. Of course, I showed you these 3 examples of intermetallic alloys, nickel zirconium, nickel gadolinium, nickel boron. But of course, you can use the database and search for these special axial ratios in all kinds of compounds. And what I found is this crystal structure of cyclododecasulfur. So cyclododecasulfur is a cyclic molecule of sulfur composed of 12 sulfur atoms. And it has this cyclic shape, and it crystallizes in this orthorhombic unit cell. And at first, of course, you can think, that's just another ordinary molecular structure. But it has the special axial ratios you would recommend for tenfold twinning. And it shows that it also has a special location for all atoms. In fact, even for some missing atoms. So this is, again, this projection of the crystal structure of cyclododecasulfur molecules, like they are shown in this orthorhombic unit cell. Then you can see that in the middle there is exactly the same surrounding of atoms, where you can add some clue atoms, at least in this two-dimensional projection. And then you can describe all these positions of these atoms by rhombic Penrose tiles. It's not the same pattern like in nickel zirconium. It's a different solution, so to speak, but it has the same actual ratio like in nickel zirconium, like for tenfold twinning. So you can describe these Penrose tiles again with this Z module, with these 5 vectors pointing towards the vertices of a regular pentagon. And you can describe these atomic positions very ideally with this kind of model set coming from quasicrystals in a way. Then you can take 2 of these unit cells neighboring and cut out this cake piece. And then you can arrange these cake pieces in this very nice, in fact, perfect manner again at the twin boundary into the tenfold twin. And if you analyze this kind of tenfold twin at the atomic positions, then you see again some spirals. And in fact, it's another generalization in the sense of the model I showed you, because now it uses 2 different kind of chiral spiral cyclic twins. You can compose this this kind of twin by these 2 different chiral spiral cyclic twins. So that's another generalization, I would say, of this of these patterns. But of course, the main question is, how do you synthesize such a thing, or can you observe such a thing in nature? Because in one way, you could say, why should you? You know, this is a very special case of some, you know, why should these cyclododecasulfur molecules order like this? But on the other side, my experience tells me that whenever there is something possible in nature, nature also does it somehow. So with this, I want to conclude my talk. I hope I showed you that these cyclic twins are interesting objects for studying, both experimentally and theoretically. I'm always astonished how nature creates these kind of patterns rather unexpectedly. I think these are patterns you would possibly not invent yourself by just thinking about them. So nature is really good at inspiring these kind of geometrical patterns. So that obviously leads into pure mathematics research, and which in turn, of course, can influence some other fields of materials research or you know, engineering, say. And for me, this all points to some general concept that you can get highly correlated structures without only always having this, say, chaotic symmetry. Of course, we know this from quasicrystals already, that there is something more than periodic crystal structures. But even in these twins, which are also long known, I think there are still some hidden patterns you can figure out. So this is my general conviction. There's much more out there just waiting to be discovered in terms of these hidden patterns going beyond, say, group theory description of these cases. With this, I want to give you some literature. I want to thank Michael Duszek for his endorsement, and I want to thank you all for your attention.
Thank you very much, Wolfgang. Please thank Wolfgang for the beautiful presentation. I'll stop recording.